I will be demoing symbol table and abstract syntax trees for our compiler using variables 5 benchmark file. We have modified this to include this function which prints an integer. Note that this takes an argument and the main function does not. This is the concrete syntax tree generated by Antler. On this we will perform code propagation, code folding, we will merge nodes, we will add node information, we'll change node instance types, and we will create the symbol table tree and update the symbol table index for each node. The result looks like this. Note that the type is not the same as the instance type, because for example this would be a variable node, this would be a constant node, this would be a comment node, and so forth. The symbol table tree looks like this. We have one root table for the entire file. Then we see we have function g and main declared in the root. Then we have for g we have a parameter, so we had to create an extra table for the parameters, which is table 2. There is a parameter a is declared. Then the bodies, they have their own table again, just like the main has the table here. The main has a index of 0 because it has no parameter. I will be showing you that code folding is working in our compiler. So I use binary operations 2 and comparisons 2. Binary operations 2 prints 2 times 2 plus 3, which is 10. So we can see here, 2 times 2 plus 3, it changes into a 10 due to code folding. 1 smaller than 2 for comparisons 2. You can see that here, 1 smaller than 2 changes into a 1. The expected output is 4 times 10 for the binary operations and 1 and 0 altering for comparisons. So if we run this, we see 4 times 10 and 1 0 alternating, so which confirms that it works. I will show you that code propagation is available in our compiler using the variables 5 benchmark file, which we have slightly modified with these two lines. X gets assigned 10, then Y and Z get assigned X, which should use code propagation. Then X get reassigned 5 and Z gets assigned to X, which should not use code propagation. So we see here X equals 10, then Y gets assigned X, but 10 instead, Z gets assigned X, 10 instead, then X gets assigned 5 and Z gets assigned X, and it did not choose to replace it with a 5. Then we run the LLVM files. We see 5, 10, 5, which is to be expected because normally it would print 10 3 times, but we changed X and Z to the value of 5.
To demonstrate arrays, we'll be using an altered benchmark file. This is the original file, and the file we'll be using is this one. We can see here that we can assign constants and variables to an element of an array. But we can also assign other expressions, like the addition in this case. Array A is a global array, but we can assign to the elements in another scope. Another thing we can do is initialize an array by using a list. If we don't use a list, then all the elements will be initialized to 0. But in this case, we use list, so we can use constants, variables, and other expressions like the multiplication here in those lists. Another thing we can do is use a variable as an index of an array. So in this case, we'll be assigning the p3 as x is 3. Last but not least, we can use other expressions as the index, like here. Now if we run this file, we should be getting these numbers, which is also what we get, so there are no problems. The for loop and the while loop are quite similar. They both have a condition which needs to be evaluated every time before we enter the body of the loop. Now, while the while loop only has a condition, the for loop also has an initialization, which is executed before we ever check the condition and before we execute the body. This is only executed once. Now there's only a subtraction or an addition. This is performed after the body and before we check the condition again. Both loops have continue and break keywords. Code that appears after these keywords cannot be reached, so we don't generate them in the LLVM. I gave them quite large numbers so we can easily recognize them in the LLVM. And as you can see, it does not appear in the LLVM. If we execute these loops, there should be 0 to 5, with the 5 only once and the rest twice for the for loop. As you can see, that's the case. And then 0 to 4 for the while loop. We have two kinds of symbol table entries. The first one is for arrays and variables. We keep all the necessary information in there. For example, the type and if it's initialized, so we can generate a warning and initialize it to 0. And if it's a constant, so that it's not updated without generating a failure. For functions, we keep an entry for each function name so we can overload. In all these lists, there is for each overloaded function one index. So in index 0, the type, init, and arguments are for the same overloaded function. We translate to LLVM by going through the abstract syntax tree in a depth-first manner. This does not mean that we evaluate each child before its parent, because we load constant variables into a temporary register. For some operations, for example declaring a global variable, we have to load the constant immediately into the right register. By loading a constant into a temporary register, there are less special cases. For variables, we can get the type and the register from the symbol table. For all the others, operations like additions and constants, we can get the type and the register from its node, because we save it in there. Another thing that is kept in the node is a label. This is especially for translating an iteration statement. Then we can put the label to which we have to jump for that node there. Each operation has its own function in which is defined how to use the child nodes. Another thing where the label is used for is for strings. We define the strings before we start translating any other nodes, because we have to put them on top of the LLVM. So we also save the string number into the label, so we know which string to use.
I will be showing you that comments are working in our compiler using variables5 benchmark file slightly modified to contain more comments, a single line comment, a comment after a statement, and a multi-line comment. We can see that the single line statement is added, the statements are commented, the comment after the statement and the multi-line comment are all there. We can also run the LLVM file to see that it prints 3 times 10, which is to be expected.
I'm going to do a quick demonstration of functions in our compiler. We can use both pointer and normal arguments. We do sort of support function overloading. As you can see, both functions have the same name. In LLVM we add the argument types to the name of the function, so int pointer here and int here. This would give problems if a user did declare functions with those names. Code that cannot be reached will not be generated, just the same with breaks and continues. That can be seen here because there's no declaration of these integers. And we can also do an implicit conversion on the return type. This return is an integer while it was declared as float, so it is converted to a float. I will be going over some of the errors our compiler can generate. The first one is a symbol error, which happens because we have defined f as a variable, and after that we define it as a function. The redefinition function error is because we have two functions with bodies defined as f3. And here in the return type changed error, we have first declared the return type as an integer and after that as a float. Here we have defined integer a twice, which is not allowed, and variable undev has not been defined before it was assigned to A, so this gives an undefinition error. This is actually a legit assignment because A is an integer and we can do an implicit conversion from an integer to a float. If the types were switched, so int b equals a float, then we would get an error as we can only do conversions to a richer type. Here we have a constant which is not an L value. We can only make pointers to L values, so we get an error. Here flat is not a legal type, so that gives an error too. And in F2, we have F2 here. It has only been forward declared, so it was not initialized with a body. So this gives an initfunc error. And F4 has not been defined at all, so this gives also an error. Array R was defined with size 2, so we can assign to indices 0 and 1. We assign to index 2 here, so we get a size error. And we also have an inclusion error. This is because we have not included the stdio here, which is needed to use printf.